First of all, I would like to say hello, sir. My name is Konara Jahat. I'm from section 1, and today I'm going to do the problem solving on the chapter 3 review question. Okay, now let's move on to the problem. 1. They want us to mark 8 of the following statements true or false. So there are 10 statements, and the 7th statement is true, and only 3 statements is false. And I will prove for you why those statements are false. First statement is B. They said that if A and B are matrices such that AB equal to 0 and A is not equal to B, then B is equal to 0. So I assume that A is equal to this matrix, yes, and B is equal to this matrix. And when I do the multiplication, A and B, so we get the 0 matrix. And A is different from B, but final answer is B is not equal to 0, which means it's different from the statement. So this statement is failed. Move to the next problem. Problem C. Next statement. Statement C. They said that if A, B, and X are invariable matrices such that X A equal to B, then X is equal to inverse of A multiplied by B. So when A is invertible, there must be exist the inverse of A. So when I do the last multiplication on both sides of the equation, we got X is equal to B times inverse of A, which is different from inverse of A times B. From the statement here, okay, is different because in matrix AB is different from BA. So the statement is wrong. The last statement, they said that if T transpose the element from 4 dimension to 5 dimension is a linear transformation, then the 4.5 matrix such that Tx equal to Ax for X in the domain of T. So by X in the domain of T, so it means X is contain 5 rows. It means X is the 5-dimension space. So when we multiply A by X, it must be from the 4 by 4 matrix, which is contained in 4-dimension space, which is wrong from the statement that said that T is transform the element from 4 dimension to 5 dimension. But by we multiply this AX, we see that T is transform X from 4 dimension to the same 4 dimension space, which is contrast from the statement J. So it means that as the result, this statement is wrong. Problem 3. They want us to compute the indicate matrix here, if it's possible. So we have A and B, but you can see here B square cannot exist because B is not the square matrix. Yes. So it means that this matrix cannot compute. Problem 5. They want us to compute the inverse of this matrix. So when B times the transpose of matrix B, here we can see this result. And to find inverse of this matrix, first we have to find the data of this B times B matrix, BT matrix. So the data is 5 times 44 plus 2 times 2. It equal to 166. So the inverse of the matrix B times BT must be 1 over 36 multiplied by this matrix. And the final answer is here. Okay, move to the next problem. The problem 7. They want us to do the outer product expansion of A times AT. So first, I have to form A into the row vector here by A1 and A2. A1 is represent the first row of A, and A2 represent the second row of A. So when A times AT, we get the matrix here. So now let's do the outer products. A1 times AT is equal to 5 and 13. And A2 times AT is equal to 13 times, and 34. So the final answer of A times AT is 5, 13, 13, and 34. Problem 9. They give us the A matrix, and when A times H matrix is equal to this matrix. And the purpose is they want us to find X. So we have the equation here, AX equal to the matrix, and I assume this matrix is equal to W. And by doing the last multiplication by the inverse of A. On both sides, we get x equal to inverse of A times W. So the problem is we have to find the inverse of A. To find this, I form the super augmented matrix here, A and I, and convert it to this form. By convert this super augmented matrix to the form, I get the inverse of A, and it equal to this value here. Now, to find x, we must multiply this inverse of A by W here, by the this inverse of A by W, and the final answer here is 0, -9, 2, 4, 1, and -6. Is the answer of x. Problem 11. So they said that if A is the square matrix and A cube is equal to 0, prove that we get this property. So in general, when I minus A multiplied by I squared plus A squared, it must be equal to I cube minus A cube. And by default, they give that A cube is equal to 0. So it means that I cube minus A cube must be equal to I cube. But everything that multiplied by I must be equal the same. So it means it's equal to I. So as we can see, these two matrices multiplied together equal to I. So it means that I squared plus A squared must be inverse of I minus A. So I squared plus A squared must be equal to this inverse of I minus A. So it means this property is true when A cube is equal to 0. Problem 13. They want us to find the basic for the row space of A and column space of A. To find the basic for this matrix, we must form this A or convert A into the row reduced echelon form. Here, we must convert A to row reduced echelon form, which equal to L. Or, and all is equal to this matrix. Here is the row echelon form of A. So the basic of row space of A must be equal to the non-zero row of all, which mean the row 1, row 2, and row 3 of all. Here is the basic row for row A. And the basic column is the corresponding columns of A to the non-zero entry column of all. So the non-zero entry column of all is column 1, column 3, and column 5 here. So we get the basic for the column A here is 2, 1, 4, 5, 2, 3, and 5, 1, 6. Okay. Problem 15. If A is invertible matrix, explain why A and AT have the same rule space. So when A is invertible matrix, it means that it must be exists of these two properties, inverse of A and inverse of transpose of A. So let X is the null space of A, and A times X must be equal to 0. By do the last multiplication by inverse of A on both sides, we get X equal to 0. So which means that if A is invertible, we got the null space of A is equal to 0. Again, let Y is the null space of AT. So it means that AT times Y must be equal to 0. And by do the last multiplication by the inverse of AT here on both sides, we get Y is equal to 0. So if A invertible, we got null space of AT is equal to 0 also. As the result, by convert these two statements, we get that if A is invertible matrix, A and LT must have the same null space, which is equal to 0. Problem 17. Explain if M times N of matrix A has a linear independent column, why A and AT is invertible. So when A has a linear independent, they must exist. The null space of A must equal to 0, which means that A is invertible. When A is invertible, there must be exist of two property here, like the previous problem. So now let X is the null space of this matrix A and AT. And when we do so, when AT times X must be equal to 0. Why do the last multiplication by inverse of A on both sides? We get AT times X is equal to 0. And by do the last multiplication again by the inverse of AT, we got X is equal to 0 here. Okay, so we can see that the null space of A and AT is equal to 0, which means that A and AT must be invertible. As the result, if A is a linear independent column, so A and AT is invertible. Statement is true. For the last problem, they want us to find the standard matrix of a linear transformation that corresponds to the clockwise, counterclockwise rotation of 45 degree about the origin, followed by a projections onto the line y equal to minus 2x. So let A is the standard matrix of T with Tx equal to Ax. So A must be equal to this property. So equal to cosine of x, sine of x, minus sine of x, sine of x, and cos of x. By x is equal to 45 degree. Plug it into the corresponding place. We get is cos of 45 minus sine of 45, sine of 45, and cos of 45. So the standard matrix of A must be equal to this value. Here is the final problem, and the present is become to the end. Finally, I would like to say thank you to you, sir, for spending your time listening to my presentation. And the meeting.